Hello, and welcome to this short tutorial on supervised machine learning and supervised text classification. My name is Wouter van Attenveld of the Vrije Universiteit in Amsterdam. What we'll be talking about today is what is machine learning in general, how do you do it properly, how do you validate it, what kind of algorithms are there, and then more specifically we'll look at doing supervised text classification in R, and we will very briefly look at deep learning. So what is machine learning? In general, in machine learning, we ask the computer to find regularities in large amounts of data where we have a specific outcome variable that we're interested in, and we want the computer to understand what patterns in the input variables can be seen as indicators for the output variables. As a small example, let's consider the idea of supervised sentiment analysis. In supervised machine learning for sentiment analysis, we want the computer to figure out which words or combinations of words can be seen as positive or negative. So where in a dictionary you tell the computer which words are positive or negative, in machine learning you give the computer a lot of positive or negative tweets or newspaper articles or reviews, and you don't tell the computer which words are positive. You ask the computer, given these positive reviews and these negative reviews, which words or which combinations of words are indicators of positive or negative reviewers. Slightly more formally, you ask the computer to model the relation between the input features and the output class. And the input features, which are can be seen as the independent variables, are the words or the combinations of words, and the output class, which can be seen as the dependent variable, in this case is the sentiment. Now, this is very similar to normal statistical modeling, right? In normal statistical modeling, you have a bunch of input variables like maybe education level and income level, and you want to understand the relation between education, income, and vote choice. However, where in most of our normal, which I would call substantive statistical modeling, we are interested in the model, we're interested in understanding the phenomenon. With machine learning, we generally only care about the predictions. We don't want to understand why some words are positive or negative. We just want the best possible prediction of whether a text is positive or negative. This also means that the models that are resulting can have thousands or even millions of independent variables that are all strongly related with each other. As you can imagine, that very often whether one word occurs is not independent of whether another word occurs. And you can also have many latent variables, etc. And we don't really care about that. Normally in statistical modeling, it would be a great problem if we have thousands of multicollinear independent variables. But here we don't care because we don't want to interpret the independent variables. We just want to get the best possible prediction. What that does mean is that we always need to make sure that we don't hugely overfit, and it means that we always need to train and test on distinct data. We'll talk more about that in the next chapter. If we look at the distribution of machine learning, a normal categorization is first made into supervised and unsupervised machine learning. And in unsupervised machine learning are clustering algorithms and dimension reduction algorithms, and topic modeling that we talked about earlier is part of the unsupervised branch of machine learning. What we look at today is the supervised machine learning. And in supervised machine learning, you have a specific outcome variable that you're interested in. And that can either be a class or a number. And if it's a number, then you basically go into regression that you probably all know from classical statistics. And if you want to predict a class like positive or negative, or topic 1 versus topic 2, then you go into classification. Now the supervised learning model applied to text means that from the input text on the top left, you first extract what they call the feature vectors. That's basically the numerical representation of those CM texts, where every text is reduced to the features or independent variables. In most cases, that will be the frequency of every word, right? So all the feature vectors together are the term document matrix that we saw before. Together with the actual class, if these are the articles, this might be for each article whether it's positive or negative or what topic it is on. Together the input feature vectors, the input term document matrix, with the output classes are fed into the machine learning algorithm, and the result of this is a predictive model. And that model can then be used to predict the expected label of a new text that of course is converted into the same feature vector. So together you ask the computer to find regularities in between the input variables, the word frequencies, and the output variable, the sentiment or the topic of a text. the result of finding those similarities is the predictive model, and you can use the predictive model to then make a prediction about the class, about the sentiment or topic of a new text or image that you feed into it. So machine learning is very similar to statistical modeling in the sense that in both cases you're trying to learn some sort of function that maps the input features onto the output value, and you want to use that so you can then predict the output value for new input features, right? So you're trying to learn a function f where y can be predicted from f applied to x. Now, as I said before, the goal of normal modeling is explaining or understanding, and this goal requires interpretable parameters. So you don't want too many parameters, and you want the parameter values to be interpretable. And the parameter values in this case would mean the betas in a regression model, right? The goal of machine learning, on the other hand, is prediction. This just requires the best possible fit, and we don't care if the betas cannot be interpreted because we're not going to be looking at the beta, we're only going to be looking at the prediction. And as I also said before, this means that machine learning models can have thousands or even millions of multicollinear independent variables. They can also have many latent variables. And in a sense, the whole machine learning thing is just one big complicated black box. We'll talk a little bit about whether that's okay at the end. But for now, let's say that's okay because we don't care about inspecting it. We only care about getting the best possible prediction. However, there is always the big danger of overfitting. Now let's say that we have data like this, right? In a simple two-dimensional world, we have a y and an x, and in this case we know that the data is generated from a cubic function of x plus some sort of error term. And this generates a bunch of points around a line that goes up. Now, if you would throw this in a linear model, you'd get a prediction like this. This is not a completely bad prediction, a linear fit, but it's an underfit, and we call it this is underfit because we know that the model is less complicated than the actual data is, and that means that there are still systematic errors made in the predictions. The prediction errors in the middle are all negative, and the prediction errors at the beginning and the end are all positive. And that is simply because we're trying to fit a linear model to a nonlinear function. Of course, a good fit in this case is a 3-degree polynomial, and we know this is a good fit because we know that the data was generated with a cubic function, so with a 3-degree polynomial function. And we see here that the blue line indeed follows the points very nicely. There are still mistakes in the prediction, but these mistakes are caused not by misunderstanding the actual process, but by this error term here. And so this is actual noise and not data that we are missing, which is good. However, if we throw a more complicated model at this, we could get a perfect fit of the data, right? So, for example, we could have a 12-degree polynomial, and we would reduce the error that we make in the prediction almost to 0, right? Because our function really neatly goes through every exact data point. And in general, if you have 20 data points, if you fit a 20-degree polynomial, you can predict every point perfectly. However, we call this an overfit, and we call it an overfit because at this point we're no longer fitting the generalities in the population, we're fitting the particulars, the particular errors in the training data. So we are fitting the error term rather than fitting the model, and we call this an overfit. And the problem with overfitting is that you get a perfect prediction of the training data, but if you get another point, for example, a point over here, that you would normally expect to have a head right about 750. If you look at the actual model, this model would predict more than 2000. Not because there's any data in this range, but simply because that's what the polynomial does. So this model will give you predictions that have much more to do with the specific training data than with the actual population. So the goal of machine learning is to find the model that is complex enough to fit the data properly, but is not so complex that it's overfitting. Now, in order to prevent this overfitting, there are 2 steps you can take. And the first is that you can regularize many machine learning algorithms and also some regression analysis, like lasso regression, have regularization parameters. So basically what it means is that the model has some sort of built-in way of trying to reduce the complexity of the model itself. This prevents overfitting. You detect overfitting, and you can do this in all sort of ways. And for example, taking the adjusted R-squared in a regression is also a way of detecting overfitting, right? So if the R-squared goes up, but the adjusted R-squared goes down, it probably means you're overfitting. But in regression, it's not such a big problem because you normally don't have millions of parameters in your regression. But in machine learning, you can have this problem, right? So just doing some sort of adjustments of your fit statistic is not good enough. What you always need to do is out-of-sample validation. So what out-of-sample validation means if you have those 20 points, you build a model on a sample of those points, and then you check how well the model does, not on the points that you gave it to model, but on points that are out of sample, right? That you didn't take in the initial modeling. And that way you can see whether your model predicts the population of which your out of sample validation is a representative sample, or whether your model predicts the training data. And so in the case of the overfits, if you have a validation sample here, you would see that the overfit model does a really bad job at predicting the out of sample data points. So you can see that the model is an overfit because it predicts the training data much better than it predicts the out of sample validation. Now, how do you actually do this? The best practice in machine learning is always to split your data sets. So you always validate on held out data, because models almost always have the tendency to overfit at some points, and the performance of the training data is not a good indicator of the real quality of your model, right? You want to know how well your model will predict new cases, how well your model generalizes to the population. And for this, you don't want to look at the performance on the training data, because that will be always an optimistic, an overly positive indicator of the model performance. You want to compare it with the held out data, which should be a representative sample of the population you want to generalize to. Now the process here in the simple case is to just split your data into train and test, train the model on the training data, and test the model on this unseen test data. And very often people take a 75 or 80% sample for the training data. You can also take an absolute number for the test data if you have a couple hundred documents, and especially if you have enough documents per label, you get a good indicator of the performance on the population. Now, a second problem is that besides the model estimating the parameters, you as a researcher very often have to choose a model and choose the so-called hyperparameters. We'll see some examples of that in the future, but let's just say that two machine learning models are naive Bayes and support vector machines, and the support vector machines also have a parameter that you have to set as a researcher that controls how badly misclassifications are counted. So as a researcher, you typically make two choices, namely what is your model and how do you tune the model, right? So how do you pick the parameters of the model? And we call those parameters hyperparameters because the betas in the regression are called the parameters. So the things that control how the betas are determined are the hyperparameters. Hyperparameters that you might know from your classical statistics are things like the number of iterations in a multi-level model, for example, or the choose of the rotation in a vector analysis. Now, most models have these sort of hyperparameters, like learning rate, some sort of regularization parameter, the structure of a neural network model, etc., etc., etc. And very often there is not really a good theoretical basis for selecting a model, right? You can't really say that the learning rate of 1 is better than the learning rate of 2, because those numbers don't actually mean anything out in the real world. So what you often do is you just select the model that performs best. But that of course brings you to a problem, namely how do you select this model? Because naively you could say, let's take 1,000 different models, test them all on our training data and see which one performs best on your test data. The problem is this model will actually perform better on your test data than it will perform on new data, because we selected the model that performs best on the test data. And so we are now again basically using our test data to choose and fit the model. So what you should do if you want to do this properly is actually split into 3 training sets, which I will now call the train set, the development set, and the test set or the validation set. But please note that in the literature, there's not a very consistent use of this terminology. So some people might actually call the second set the validation set, etc. So a little bit more graphically, and what you do if you're doing machine learning is the first step, of course, is your data acquisition, get the data from somewhere. And the second step is your data cleaning to get the data and the shape that you can use for the machine learning. This is normally actually the point that you spend most time on, even though it might not be the most interesting thing. Now then, what you do is you select your training data set, so that might be like 75% of your data. You use that to train a machine learning model, and you test the model against your, what they call the test data set, which I would call the development data sets. And so this is a second set of data that hasn't been used in the training that you test the model against. Now, based on this test, you adjust the model parameters, or you have 100 different configurations, and you test the model against the test data sets, and you pick the best model. So the result of this part of the process is that you have the best model with the best choices for the hyperparameters trained on your training data sets. Only then you use that one model against your, what they call the test data set, the held out data, the validation data, and so the data that's not been used in the whole process so far. And this gives you an unbiased estimate of how well your model will do in the real world. And if you're happy with that, then you can then go and deploy your model and actually use it to predict sentiment or topic or whatever on unseen documents. Now, of course, splitting your data into 3 means that you have less data left. And that is a shame, because the more data you have, the better your model will perform. So one thing that you very often do for model selection is to use cross-validation. And what it basically means is that you take your data and you don't take the validation data here. So this is only the 80% or 90% or whatever that you can use for developments. You don't split it into a training set and a development set, but you instead split it into a number of chunks. For example, 5 chunks like this, right? And then first you train it on chunk 2, 3, 4, and 5, and you test it against chunk 1. Then you repeat it, but you train it on chunk 1, 3, 4, and 5, and you test it against chunk 2, etc., until you have used every chunk once as the testing set. And then you aggregate your performance on all these test sets, and that will give you a good estimate of the performance. And the advantage here is that you have used every data point in your testing, so you have a better idea of how well the performance actually is. The problem is that you've used more computing time because you've now run 5 models instead of 1 model. But the good news is, because some of those algorithms are not deterministic, so actually running the model a number of times and aggregating is a good idea anyway, to make sure that it's not random variations, but it's actually the underlying performance that you're looking at. Now, a final issue is non-determinism. As I said, many of those machine learning algorithms are non-deterministic. That means that if you run the same model twice, you will get a slightly different outcome. You've seen that with topic models already. Topic models are non-deterministic, and actually also any model that uses iterative estimation, like a multi-level model often does, is also non-deterministic. And that means that you have some sort of random initial state or some random change in the parameters that determines the outcome. And if you are using a train test split, then of course also the choice of splits will determine the outcome. And the problem there is, of course, that your research is not replicable, and the other problem is that the outcome might actually be a result of the randomness rather than a result of the underlying data. So the first solution is that you should want to normally set a random seed. I'm using the set seed command in R, so that at least if a researcher tries to replicate your paper, they can replicate it perfectly. And so this at least gives them the guarantee that they are looking at the same data that you did. To get a more valid outcome, what you should normally do is actually repeat the whole experiment, for example, 10 times, and then report the average performance and also the standard deviation around the performance, so you have a good idea of what part of the outcome is actually determined by those random changes and what part of the outcome is replicable. Now, the final point I'd like to make is to talk about the representativeness of the test data. So if you split your data into training data, development data, and test data, you want your test data, your final data that you're going to test against, you want that to be sufficiently large and representative of the population. And from normal measurement theory, this is actually the same as taking a sample of the population for a survey or an experiment or whatever, right? You just want to know that what you report about the sample is representative of the population in general. So you can also use the normal ways of determining the right number of units there. There's 2 things you want to take care here. First is if you have outcome classes that are pretty infrequent, right? So maybe in political news, there's a lot of negative news, there's a lot of neutral news, and there's not that much positive news. The problem is if you take a random sample, say of 200 tweets, and only 3 of them are positive, then you know that that is not enough to actually give you a good idea of whether your model is able to find positivity in general, right? It will only tell you whether your model is able to find those 3 specific positive cases. So always look at the distribution of your outcome classes, and if needed, you can take a stratified sample to make sure that you have a good estimate of each of your output classes. Of course, it's difficult to take a stratified sample if you have a dependent variable that you can't actually measure, and that's why you are making machine learning in general. So that might mean you just need to oversample, or you want to use a secondary strategy to find tweets that might be positive. A second problem is that sometimes what you are predicting might be different from what you are training on, right? So for example, if you're making a model to predict news in the future, you don't have data from the future yet, right? So if you want to have a model that runs every day to show you whether today's news is positive or negative, we don't today have training data for tomorrow, right? So you don't really know whether your model, based on current data, will be able to predict into the future. And the same for contextual differences. If your training data is, for example, from one specific newspaper and you want to predict articles from another newspaper, or you are training on Facebook data, you want to predict Twitter data, whatever, you never quite know whether your estimate is good, right? Because your testing data is not drawn from the same population as you're interested in. In general, this is called transfer learning, in the sense that you're trying to use data from one domain to predict from another domain. But I will just give a small easy fix maybe for the problems that we often look at. So for example, if you have 10 years of data and you want to predict next year's data, one way to get a good indication of how temporarily dependent your model is to, for example, first train on only the first 5 years of your data and try to predict the last year of your data. Of course, that will not give you a guaranteed answer to how well your model will do next year, because maybe something is going to happen, like a COVID pandemic, that is going to really change the way news is made, right? Or the election of a president or whatever. And things can happen in the real world that change this relation. However, it will give you a good idea or at least a first idea in general of how dependent your model is on time or domain or context, etc. So that is something you can do as a robustness check to see how well your model might do in the future.